So I think we're live across the board. Yeah.
Let's make sure this time.
Well, I'm gonna double check. I got check marks everywhere.
Okay, good.
But I'm gonna just jump on YouTube here and see if.
What ended up happening with the last one?
So it was live on Twitter and LinkedIn.
Yeah.
But not on YouTube. So what I did is I took the recording once I've got it and uploaded it to YouTube and made it live. Oh, yeah, we are live. The problem is I got the overlay on. There we go. That's what I'm wondering why I was just seeing the. Anyway, yeah, I was at Discovery X this week, and I enjoyed that. Like I was saying, I met some people. I've seen some people I haven't seen in a while. Angelo Del Duca of York Angel Networks, and you were talking about when I had you both come out to the C&E pitch competition a few years ago. I just don't see Angelo enough. We talk, and we always talk about doing stuff, and then I don't follow up. So, but we get to see you once a year, and then like Stuart Brown from PiCap Venture Partners. He's a pretty busy person, but he's been around and supported Toronto Start since the beginning, and he's been on this whirlwind tour and whatever. And I think he teaches at Schulich, I think now. Was great to see him. I haven't seen Kevin, the story architect. I saw him. I saw some my friends at Porch, and a bunch of others. So it was great. It was a great. I don't really like to go sit and watch presentations like a lot of people do, but that's fine. I mean, I understand that having hosted a lot of events, I just don't like doing that. But I like going around and talking to people, talking to the startups that are there. The coffee line was crazy. I should have took a video of it, and there was like 2 baristas working when one person taking the order the whole time for the whole conference, and the line was like 100 people long, like for the whole thing. I'm looking at the I walked by, so I really feel sorry there. Like you can just see that they've been nonstop. They're so haggard 2 3 o'clock in the afternoon because the line has never stopped all day.
I think you and I are the same when it comes to like the presentations and stuff, because we're so involved and we're so on top of things. Like it's information a lot of times that we already know, unless it's like some new kind of tech or something like that. But
yeah, not to be like, I know a lot of the speakers, and because they've spoken for me or I've had them present or whatever. Not all of them, like Randy Zuckerberg, I didn't know, and a bunch of the other ones. But I know a lot of them, and I know we integrate into the same circles and all that kind of stuff. So it's just one of those. I'd actually rather talk to the startups and the individuals there, and I really enjoyed doing that. It was a great time. So I'm sorry you didn't get a chance to go there, and I missed Alex from Consulta. We were supposed to try and connect, but that didn't happen.
Yeah, she was there both days, I think. So
yeah, are we ready to jump into this?
We're ready. Let's jump in.
So I want to start with saying welcome back to FutureTech, your weekly source for the latest in tech and innovation and business. I'm the startup coach, and as always, I'm joined by my co-host, John Irwin. How you doing today, John?
I'm doing good, Craig. I'm watching the Bitcoin halving countdown to 12 hours, 21 minutes, and 49 seconds. So we'll have to see.
What's happening then?
So the Bitcoin is having every 4 years, about 4 years.
Okay, the halving. Sorry,
yeah,
I missed that.
Or the halving, or whatever, however you want to pronounce it.
And I hear something too. I saw some in one of the newsletters I get that there's expecting it to go to 100K post halving. So we'll see how that goes.
People have predicted 100K last year, 100K 2 years ago, but I'm just, you know what, I'm curious to see what's going to happen this time. So is this the third halving? Fourth halving? I can't remember. Anyways, 12 hours, 77 blocks left. Current price 65,000.
Yeah, let us know in the chat if you are into Bitcoin and what you think it's going to go to after the halving. In the let's just say within 2 weeks after the halving, it'd be interesting. But we've got a lot to talk about. This first article is, if this is the one that first got up, it's not the one I first got up, but it's the one we're going to talk to first. Apparently,
that's why you're moving things around on me, but that's
I'm moving it around. We're going to talk about the Trillion-Transistor GPUs.
Yes.
You know, GPUs are all the rage. We saw that Sam, the guy from OpenAI, sorry, is going out and trying to raise, I think, $7 trillion to start a EFAB for a GPU company specifically for API. We see all these major investments, then we see this Trillion-Transistor GPU. What's happening?
Well, makes sense. And just before we jump into it, there is a Canadian company, Grok, who was getting into the hardware, building a chip. And I think that they've pivoted, and now they've pivoted to more of a SaaS model. So it'll be interesting to see how what Sam Altman does. Obviously, he's a lot further along and has a lot more collateral and clout. But Grok they did some really cool stuff. Yeah, so right now we pretty much only have NVIDIA who can produce these massive or these amazing GPUs for AI and other complex problem solving. So the article itself provides a look into semiconductor innovations that are going to be needed to reach a 1 trillion transistor GPU within the next decade, which is critical to enable the next generation of AI capabilities. Not only that, the other issue we have, and sorry to go off on a tangent, but we need more training data as well to help with these AI capabilities. So that's another problem that we won't talk about now. But so it talks about key enablers that will be advanced, like 3D packaging methods like TSMC's CoWoS or SoIC, which allows stacking and connecting multiple chiplets. It overcomes the limits of conventional lithography-based manufacturing and can integrate systems with massive transistor counts. So what's equally important will be continuing device-level advances like new materials. So EUV lithography down to 1 nanometer and below, novel transistor architectures tailored for AI workloads. So the coordination of chiplet integration, system architecture, software optimization, and transistor improvements will drive energy-efficient performance. So the expansion beyond conventional 2D scaling into full 3D integration is pivotal for the revolution in the industry. It opens up architectural possibilities that we're only beginning to explore. So it's really cool, but in order for us to move forward, so we're talking about new transistor materials. So we're going to need new transistor materials and this gets into some stuff that we talked about before, nanosheets, nanowires, CFETs. That's going to enable scaling at smaller nodes that's required for high transistor densities. And now we're getting into Moore's law, right? And pushing Moore's law.
Well, hasn't Moore's law slowed down?
Yes, Moore's law has slowed down. But we were supposed to hit a limit, I think, at some point. I think this was years ago. And I think with the new technology that we're developing, so just for those that don't know, Moore's law states that the number of transistors on a microchip doubles about every 2 years, while the cost of computers halves. So in other words, the speed and capability of computers are expected to increase every couple of years, and we'll pay less for them. So it predicts that computers and machines that run on computers and computing power all become smaller, faster, and cheaper with time as transistors and integrated circuits become more efficient. So it's not a scientific law, but rather a projection based on historical trends. Obviously, this is based on silicon-based transistors and different things like that. But as we talk about different kind of materials and things like that, who knows if law is going to be broken or if it's still going to remain the same.
Yeah, this is interesting. I can see our need for it, and this is what we're talking about here, is that, our for example, training GPT-3, for example, required the equivalent of 5 billion operations per second of computational data for an entire day. So just imagine that.
Yeah, and the other thing too to note is that we talked about TSMC, and I could be wrong, but I think TSMC holds a monopoly over producing chips as far as the technology and the size. But it's crazy.
So where are we now? How long is it going to take us to get there to do this layering and get to, like we talked at the beginning of that Sam Altman's trying to open up this new GPU fab. What are we talking about here? Will he be able to be implementing this in a few years, or any of the companies, or is this something that's a little farther off?
So, in order for us to get there, there's a bunch of things that need. So the technology exists, right? This 3D advanced 3D packaging, okay, but there's some key challenges that they need to overcome. So they need to overcome thermal management. So if you think about it, right now we do, well, for the most part, it's 2D kind of wafers, right? And so if you're stacking dies, if you're stacking these wafers, it leads to higher power density and localized hotspots that must be dissipated. So we're talking about taking a 2D model, changing it into a 3D model, a 2D model that already has like heat and power and issues, and then adding layers on top of that, right? So I don't think we're too far off. I would say maybe 2 to 5 years based on where we're at currently with the technology, as long as there's no big issues that come into play. But there's going to be, they're going to have to develop dense vertical interconnects between the stacked dies as well, while ensuring reliability and yield. There's mechanical stresses, there's die thinning, there's die-to-die alignment, again, supply chip maturity, there's a bunch of things that need to be overcome. So I don't think, I know we always say 5 to 10 years in most of these that we talk about, but I'm thinking we're 3 to 5.
Well, we're talking here about, silicon photonics, like we were talking about. I think it was last week, might have been the week before, when we were talking about the new internet speed breakthroughs going through optical fiber, packaging this kind of excess bandwidth right in, together with the GPUs and the CPUs, are going to allow it to scale up. What are, like, right now, let's face it, the AI factories,
Yeah.
the GPU houses where all this compute happens, that they call it, is very power intensive. If we take that up to the next level, and put a trillion transistors into the same data farms, what kind of power consumption are we have to scale to?
I honestly think we'll be, if, like, obviously at the start, well, they'll be more power hungry, but because there's more transistors, I think there's an opportunity to be more power efficient. It's just like when you have a bigger engine, right? If you want to go faster, you're not, yeah. So that's a bad example. Let's talk about this. But if you have more transistors available, there's likely potentially less power that could be used, because you have a lot of different options, and it's not going to be maybe pushed as far as the current chips, if that makes sense.
Yeah. So when you're talking about stacking these things, at what nano level are we talking about? Like, the latest stuff from silicon, from Apple's 3 nanometer, we were talking about 2 nanometer. Some of this stuff is 5 nanometer, 4 nanometer. We're talking about here, when we're talking about 3D stacking, are we talking about, 4 millimeter on 4 millimeter? Or what are we talking about?
I don't know. I didn't see that in the article, but I think there was something talking about 1 nanometer at one point. And so, and again, so we're talking about a new technology, like a new chip design. So we might have to go to a larger wafer size at the beginning, and then get down to one nanometer. But who knows? The thing is right, all we're doing is we're stacking them on top of each other. We're stacking them dies on top of each other. So based on, we could stack based on what the current size is, if that makes sense.
Yeah, I guess we're seeing a comparison here on the screen now for those who are watching, which is talking about the current, where we're transistors per processors are currently increasing at 1.73 times every 2 years. And if we're using this chip-to-chip bond density technology to increase 1.74 every 2 years, you get to, what's this, 339, 786 billion on a per square meter versus 1154.
Yeah. So I should correct that. To get to the 1 trillion is going to take a while, but to this 3D technology, I don't think we're far off. And you can see it here, even here, 2021, they've got 20,000 on one. So they're already starting to get there. They're already starting to produce them.
And to make a correction here, this right side happens to be apparently per processor, not per square millimeter. So we're not really comparing the two
we're
here.
not even comparing apples to apples.
Yeah, let's just transistor count per processor, and then you've got a trillion transistor per square millimeters. I guess it depends on how many processors you have that you start. Like this is saying, this is in the billions, 1154.09 billion transistor count per processor.
Okay. So, that makes more sense. Yeah.
So this is very interesting. Okay, we're talking. Great. Here's some stuff on energy efficiency, because I was just kind of, we're always trying to make the environment a better place, and how do we not destroy it yet have all these wonderful things we want. Well, the increased energy efficiency performance threefold over the last 2 years, which is great. But I don't know. From low end processing, absolutely. The power saving modes of these new ARM technology and stuff is much better. But does that happen when your CPUs are running at full power?
No, and that's never gonna. But the thing is, and that's kind of where I was getting at. Thanks for that. Is you're gonna have obviously more transistors and to work through, and so lower power tasks are going to be more energy efficient on these chips, but they're going to be able to handle more power intensive tasks, which obviously they're going to be more power hungry than the current chips when you're using those tasks, because the current chips can't do those tasks, if that makes sense.
Yeah, and that leads us to this part where we're talking about, this is a Meade-Conway moment for 3D integrated circuits. So for those of you who don't know, that was they designed the original CAD, the tools you needed to design the chips and stuff. And we're coming to that moment where we're going to need new tools to design these 3D chips, I guess.
Yeah.
To make this happen, and this is going to change everything.
For sure.
So it's on its way. An open source standard called 3D Blocks apparently has already been embraced. So great.
Yeah. So again, this is with the current type of architecture, right? And so the thing that I'm curious about is, are there other architectures that could come into play and just disrupt this whole industry? Like, is there something completely that we haven't talked about, that we haven't explored, that could potential, and who knows?
There's always other stuff that could be happening, but I guess the question is, when we get to quantum computing, are they using these, or are they using completely different types of nanoscale hardware?
It's a good question. I don't even know what they're using for the quantum computing,
because that feels like, as you'd like to describe quantum computing, is like it can all states at once and stuff. That's great. You would think that if it's capable of doing that, it would be capable of doing a lot more AI functionality than, say, a high-end CPU.
Absolutely. Yeah. The thing is so just based on my understanding, like, I know that quantum computers, they use specialized chips that are different from traditional classical computing chips. I don't know much more about them, but yeah, I think there's a bunch of different types of chip technology that are used, and they're proprietary built. So like IBM, Google, like they're all building their own proprietary chips for quantum computing.
And it's interesting. Oh, absolutely. Like, I haven't talked to any of them specifically. There are some interesting hardware companies in Canada dealing with quantum, but I've talked to a few of the ones that were related to a blockchain that were building blockchain specific chips.
Oh, that's interesting.
Like Epic Blockchain and a few other companies. And this was back in the day. I don't know where they went, but they're either basically hardware to do the algorithm specifically or to work with that are specific silicons designed specifically to work with the blockchain and make stuff work faster. So so all that stuff is interesting. I love where all this is going as we get more and more systems on a chip technology, and I think the world's starting to embrace moving away from an Intel CISC architecture and moving to like ARM. Seems to be what's happening now. We'll be seeing where that goes, and that ARM leads to all this more interesting system on a chip stuff where you can do more specialized hardware where the software is actually in the hardware.
Exactly.
So this becomes very, very interesting. Any last words before we move on to the next one?
Yeah, just to talk about the Canadian company Grok. So they develop specialized AI accelerators focused on inference workloads. So they've got a Grok chip architecture that they designed specifically for efficient deep learning computations like convolutional neural networks. So I know that they developed that and now they're pivoting, but they've got, just talking about a cool Canadian company in this whole thing. So that has some promise, but that's it.
Do you know their website?
GROQ.AI. Grok with a Q. Yeah.
There you go.
Not Elon Musk's Grok.
And did I hear something come in? No. Perfect. All right. I'm seeing if that comes up. If not, if it comes up, I'll share it. Otherwise, we're moving on. I think we're moving on.
Grok Canada. I'll tell you. Yeah, grok.com, GROQ.com. But now the site is a little different. But anyways.
So the site is a little different. So the next article we want to talk about is vacuum. Infinite vacuum energy from space and the Casimir effect.
Casimir effect. Yeah. This is interesting. So the article that we're talking about from Popular Mechanics provided it's an introduction into the pioneering work of Hendrik Casimir in predicting a tiny force between two metal plates from quantum field fluctuations. So what's interesting is that it proves the existence of quantum vacuum energy. So in the article, they're talking about the direct effect. It's really minuscule, but it does open doors to potentially harnessing an unlimited resource. What obviously further research is needed. Again, we're talking about theoretical pretty much. So with further research, the force could enable microscale levitation, frictionless bearings, precision manipulation of nano devices, and potentially even energy generation. But practical applications definitely require a lot of knowledge gain that we're going to have to do a lot more. But the ideas include using metamaterials to better exploit geometry, surface plasmons for resonance amplification, and phase transitions to trigger kind of large force differences. So the field itself needs more investigation into how the forces play in quantum phenomena. So there's overall, like, the prediction based on infinite quantum nodes is a whole new avenue in fundamental physics. But again, with this one, we've only scratched the surface of what's possible. So we're going to have, in order for this to even have any chance, we're going to have further breakthroughs in nanofabrication, exotic materials, quantum coherence, a whole bunch of further breakthroughs. So there's a lot to unravel here, but it's an interesting how we might be able to tap into hidden quantum energy here.
So let's get into this a little bit. What are we talking about? We just start plugging, have a space elevator. We run with our electric cable and plug it into space. How does this whole thing, the Casimir effect, work? And how much unlimited? Is it a little energy forever, or is it a lot of energy as much as we want?
Yeah, so here's the thing. Like this is where I was thinking it was going, was getting the hoverboard from Back to the Future going. But yeah, as far as this, like there's so much to unravel here. There's a few key reasons why this is potentially possible. So the vacuum. So it's an empty space, right? So because a vacuum is devoid of any energy or physical substance that could induce forces. So a force arising from a vacuum is kind of paradoxical. So it's, and again, we're talking about something from nothing. So we're essentially trying to harvest energy from an empty space. And that violates our intuition from thermodynamics and experience that energy must come from identifiable sources. So there's so many things that and we're talking about, again, we're talking quantum level. So we're talking very, very tiny forces. And the forces that have been produced, there have been tiny forces that have been produced to date. But yeah, we're definitely going to have to explore this a lot further.
Yeah, I'm just glancing at a few of these other articles that are talking about that. Yes, it is infinite according to quantum theory. It's actually packed full of energy. Is automatically regularized to zero value without using any pre-purpose built. Yeah, so we can. It sounds really interesting, but is it really going to lead us in, let's just say, the next 50 years to infinite energy?
I don't think the next 50 years. I think we're talking, unless there's a breakthrough. I think we're talking 100 years if we're still on the planet by then. So like although it's been experimentally verified, right? But it doesn't provide a means, and we're talking about, and the article here talks about like light speed travel and stuff. This doesn't provide a means for light speed travel because of the special theory of relativity. It's pretty much impossible for any object with mass to travel at or faster than the speed of light. But then we also talked about in a previous episode that they did find a potential to wrap something in a bubble in order for it to, I think,
warp drive.
Yeah, warp drive. Yeah.
And then you were talking about some sort of weird slingshot effect, but I think that's just to get stuff in orbit.
It's a company. It's a viable company. That's how they launch satellites, using centripetal force.
I want to see it. It sounds like that medieval meme with the people doing the it's not a catapult, it's the French one where the thing swirls around and throws it. Yeah, you know what I'm talking about. I can't remember what they're called now.
Sorry, it uses centrifugal force. Sorry, not centrifugal force, but it's called spin launch.
Spin launch. All right, we'll have to take a look at that. Let's not get too far off topic, chasing the stuff around. Why, if we know it's there and it's been proven, why is this such a challenge?
Because we don't have the materials, we don't have the knowledge. So there's a few factors. So small forces, because first off, small forces, quantum forces involved are tiny, so they're equivalent to the weight of a bacterium or even less. So detecting such minute forces requires extremely sensitive equipment and isolation from environmental noise. So we'd have to essentially do this deep in the earth almost. So the other thing is close proximity. So enable to generate measurable Casimir forces, the objects must be positioned unnaturally close. And we're talking 10 to 100 nanometers close. So keeping two macroscopic objects perfectly parallel at this scale is very technologically demanding. The other thing is, if we're talking about it at that scale, surface properties. So the interacting materials, they need a super finely controlled surface smoothness, cleanliness, and conductivity to really observe the effect reliably, which requires meticulous preparation. Then we're talking about quantum coherence. So maintaining quantum coherence between the objects is essential, but it's hard to achieve on macro levels in a noisy lab environment, and it tends to suppress the effect. So there's a lot of factors that make this super challenging to measure and to work with.
Yeah, I'm just throwing up the video here. If people are watching, this is the spin launch website that they're talking about. Just because it's interesting and we were talking about it. So,
Yeah.
What makes the prediction of a force between the plates from vacuum fluctuations so counterintuitive? Why doesn't it work the way we think it works?
Well, yeah, there's a few reasons. There's action at scale. So the plates physically don't touch. So an invisible force between them defies our intuition about locally and contact forces like magnetism or gravity. And then again, we're talking quantum scale stuff. So the microscopic structure of the quantum vacuum is hidden from our direct perception. So quantum effects like virtual particles populating an empty space are not intuitive concepts. And so the deeper we dive into quantum, the more we learn about these brand new concepts for things that we have no real understanding of, and how to measure or how to observe or things like that. So again, the idea of harnessing energy from empty space, it violates our intuition of thermodynamics. It makes no sense classically, because no effect like this appears in classical electrodynamics or other physical theories. Only quantum field theory predicts this. So mathematical origin. So the Casimir force arises from a mathematical subtraction of infinities, not from simple mechanical picture. So it makes the effect seem almost, I hate to use this word, magical. And
Magic.
So again, all of this stuff that we're talking about when it comes to quantum, we're almost, if you think about it, we're almost in that era before Tesla and Edison and all those guys, and they were coming up with all this new technology based on physics, not quantum physics, where people thought it was magic at the time, right? So we're getting into that, but I think we're years and years and years away, and you're still playing the spin launch video.
Well, might as well while we're chatting. Because it looks pretty cool, and I was the doubter saying, yeah, whatever, and then here we are. Like, okay. Yeah. So I gotta eat my own dog food when I.
Just the thing to note with spin launch is you cannot have a human person.
No, anything living would be dead.
Yeah, anything living in that. Yeah.
You got to be spinning around. What's the G-force? Do you have any idea? I'm curious.
I have no clue.
We'll have to do a one just on this, because I'm really curious.
Do it.
To what the G-force speed and how fast things are at launch. Like you're literally just throwing a rocket into space. Here you go.
Yeah. And we're talking, so in order to escape Earth's gravity and the gravitational pull, there's a certain speed or a certain metric that you have to achieve. So it's pretty interesting.
So back to infinite energy and achieving light speed, which is what they're saying. And we're talking, I read science fiction. We talk a lot talks a lot about this. Most of the stuff gets maybe to a tenth of light speed from all practical. So,
it's actually funny because I don't know if you watched the new show, The Three Body Problem.
I read
really
the book.
Cool stuff. Okay. So they talk about light speed and but again, that's science fiction. That's a TV show. And they were talking about how they would have
they're 4 light years away, but it's going to take 400 years to get there, even though they can go 1/10 the speed of light.
They were going to send a probe with someone's brain. I think that's how they were going to do it, in order to send someone or send. Yeah, but anyways.
Yeah. Anyway, it's different. The show is probably different than the book, and from what I understand, they took some things from the second and third book to put it into the first season. So I'm not 100% sure. So you probably know or have more insight than I do, because I just read the first book. Anyway, it's really interesting. Like when you're talking about people in these things, we can't accelerate at any speed. It takes years to get up to that speed is part of the problem. So I go back to unlimited vacuum in space, and I feel like, is this a trickle or is this like, the volcano of energy? When I flick the switch, is it coming in, or does that depend on how we build this interface between the two?
Well, there's a theoretical basis for this, right? So there are theories in quantum field fluctuations. Like there are proven theories. Now there's technical challenges. So new physics may be required to induce or enhance the measurable energy shifts. Producing macroscopic work, like there's tons of challenges, but there's future prospects. In order for us to achieve future prospects, we're going to need breakthroughs in metamaterials, nanofabrication, quantum coherence, and other advanced technologies that we might not even know that we need yet. But there's significant gaps. So directly converting vacuum energy to electricity may prove elusive. Who knows? So yeah, this is super, super, super early. It does promise some potential, but the realistic outlook is we have so much more to learn on this. Like this is one of the earlier ones that we're covering.
Absolutely. And this is another article here talking about how scientists are currently working on an experiment designed to show that it can even slow down light and deflect it, a vacuum. So this is interesting. So being able to, the only thing that we've seen to be able to do something like that is black holes, as far as I know, to bend or slow or move light.
Yeah. Well, yeah. But light does refract in materials currently.
Oh,
but
of course. Refracting is
yeah.
different, but we're talking about a straight beam that when
Yeah.
it goes near a black hole does this little whoop
Yeah.
or gets sucked in or whatever. Now we're talking about they can slow it down or deflect it, which is, and I say deflection, which is interesting. Like what's deflect it with vacuum energy? This is what we're talking about here.
Yeah. Speaking of black holes, though, did you know that our modeling has changed because of a movie?
You're not going to go back to that 5-dimensional under the staircase movie, are we?
No, but just the modeling of the black hole, not anything else to do. That they were super accurate with the modeling and the depiction of a black hole. That's
you're
it.
You're not talking about Disney's original black hole movie.
No,
With that
oh
little
my
robot.
God,
That was great.
A dark movie, jeez. And they also had a pinball machine for that movie too. But anyways, we digress.
Of course. So light is supposed to travel in a straight line at the light speed in a vacuum. It will be slowed and deflected when the latter is subjected to strong magnetic fields. So it's interesting to see what they're trying to do. So these guys are trying to deflect it and use even the earliest version of quantum mechanics at the beginning, equations, new theory introduced mathematic terms that baffled. It's a paradox in energy, like you were saying. So
yeah,
I'm very curious as to how quickly we can do. Yeah, magic. We got a little magic wand from our LinkedIn user here.
yeah.
That's exactly it. Quantum. We got real physics, and then quantum physics, which is magic. So we
Magic
just,
physics.
yeah, it's magic. And I'll believe when I see it, but I'm curious as to where all this going. Hey, this is an artist's impression of quantum vacuum fluctuation. Okay.
Yeah.
All right.
Just
then.
like any picture that's taken in space, how they they render it, they add all the like nice colors and stuff that we can't see. So
yeah, this is interesting because it changes everything long term. If it's 100 years, 200 years out, if we're talking about going to the moon, which we were talking about mining on the moon, if we're talking about uh, taking humanity out into space, if we can actually take energy and power ships and or cities or civilizations through the energy of the vacuum, that becomes infinitely more likely.
Yeah.
Anything else you want to add to this one?
No, this one's really magic technology, but really cool stuff though. That when we're talking about energy and space exploration, this if we can get something there, then yeah.
Amazing. So let's talk about this next thing, which I'm always kind of skeptical about because these things happen. I've seen these happen a lot. And I've never seen anybody really. I hear they get regulatory approval and then they never actually come to market. Somebody sues them. It's not working. This and that's happening. But here we are, continuous non-invasive glucose sensing on the horizon with development of new optical sensors. So basically it's optical, continuous, non-invasive. So you don't need to test yourself all the time because it's constantly on there. So you just get an alert when you need to do something.
Yeah, this is cool. And again, we've got a diabetes epidemic problem in North America and across the world. So this is a new development in glucose monitoring technology. So they've created a miniaturized optical sensor that can provide, like you said, continuous non-invasive glucose measurements, which could eliminate the need for fingerprint blood tests and those adhesive patches that currently monitor glucose levels. I didn't know this until recently, but those patches have to be removed every few days, and they are hell to remove. Like they hurt a lot, especially someone with sensitive skin. So this is cool. As far as the technology goes, the sensor is only 5 millimeters wide. And it utilizes a newly discovered infrared signature of glucose to differentiate it from water signals. So the biggest thing here is that separating glucose from water has been the biggest obstacle in developing a small wearable optical glucose sensor. So what they did was the sensor itself was tested on glucose solutions and blood plasma, and it showed the ability to detect glucose, Jesus, in the range of 50 to 400 milligrams per deciliter. So that covers the normal human glucose levels, and it's comparable accuracy to larger benchtop devices. And the way it works, apparently, what they're saying is it uses an LED light source and laser pattern flexible copper circuits on a thin plastic film, so which makes it a millimeter scale and very lightweight, and it allows the potential for integration into smartwatches or maybe skin patches for 24/7 glucose reading. So maybe our next Apple smartwatch will have a glucose reader. So it's good because and I did look up a value, and I think it might be in the article, but over 460 million people suffer with diabetes, type 1, type 2, and we can debate whether Alzheimer's is type 3, but yeah.
Yeah, we'll take a look as we go. There's a comment I'm going to get to from our users, but non-invasive glucose sensing as a target for almost 30 years. Like, this is why I keep saying, I keep hearing, oh, we got this. It's going to be in the next Apple Watch. We're going to get this. We're going to do that. Or next thing, I got this little optical set. And none of it ever really gets approved. We're still doing invasive glucose. This is why I'm always skeptical on this. And we got this note just that's going to take us for a little bit of a tangent here. Okay, you guys gave me an idea about the way that we're molding stones in ancient Egypt. There is a frequency that can destabilize the weak electrical force to literally allow any molecular combination to be puttied. I've seen that in certain sci-fi. I don't 100% know if that's true, but I do believe, if we look at a quantum level, we're all based, there's harmonics that are at the very core of us that we could, I believe that we could easily disrupt stuff like that. What about you, John?
Yeah. What's the movie that where they did that, where they were using RF frequencies to kind of to do drilling? I can't remember now, but
you're not thinking of Armageddon?
No,
maybe they had to use diamond drill bits or whatever for that.
Was it the other one that came out around the same time as Armageddon? It was something, but anyways, we could get into the universe frequencies and all that sort of stuff. I haven't really done some research into that, but yeah.
So apparently it's demonstrated its ability detecting glucose levels at 50 to 400 milligrams. You said it was 5 nanometers, the camera?
The sensor itself is 5 millimeters, not nanometers.
Millimeters. Okay.
Millimeters, yeah. And then, so the thing is they have filed a patent, which doesn't really tell you much, but that does mean that they might have something. If they filed a patent. If they get the patent, then that'll tell us something more. But so just to get into just some more details, the sensor itself operates in the 1600 to 1700 nanometer, which is near infrared range. So it analyzes. So in this range, they were able to identify 4 distinct absorption peaks specific to glucose, allowing it to be differentiated from water.
Yeah, and it looks like they're using it via a Bluetooth, allows it to use a coin battery for monitoring, so it lasts a while.
Yeah.
Probably can be recharged. So yeah, you could probably eventually put this. The diode's only 110 microns thick.
Yeah. So the thing to note with this, though, is that the only computational simulations were done to model light penetration through skin and optimal sensor placement for future clinical testing. So I think what that means is based on what I read, is that they tested it directly on blood, not as a wearing it on the skin, if that makes sense. So detecting it from blood as opposed to and they're saying it's non-invasive, but I think that they that based on what I read is that they've only done simulations in the modeling to figure out the light penetration through the skin itself.
Yeah, so it's external. It sounded like you're saying it was internal for a bit.
Not internal, but like it only works directly on blood or plasma. It doesn't work through the skin, I don't think. I think it's
okay. What you're saying, they're working on it now to get it through the skin. Wow. Okay, so we'll see. Non-invasive nature, glucose has the potential to improve patients' compliance, reduce skin comfort, lower risk of infection. Yeah, I mean, I think non-invasive and continuous monitoring when it drops. The problem with obviously any sort of continuous monitoring is power.
Yeah.
Because with these things, it looks like you have to shine a light.
Yeah.
And then the camera kind of scans the differences through there. So you're constantly scanning, whether it's, once a minute, once every couple of minutes, what does continuous mean exactly? And taking those pictures and analyzing them and figuring out where you're at.
Yeah, exactly. So the LED light source, that's what shines the infrared light. Oh, actually, no, sorry. Yeah. It does work through the skin. And the light can penetrate through the outer layers of the skin. Yeah.
Cool. That's what I was reading here. And I was just like, hey, I wasn't sure.
I misunderstood. Yeah.
And, we'll have to see. Things like a watch is great because you have it, but it might not be optimally placed for monitoring blood.
Yes, exactly. So it might have to be like a patch that's like a powered patch or something separate. But again, newer technology, and in its infancy as far as actually something that could potentially work. So as technology develops, it could potentially get integrated into a watch. But right now, I don't know.
This is great. I love to see the technology moving forward because we can, once you have this kind of technology, it'll help all these people. But there's a lot of other situations where now we can be monitoring the blood for all sorts of other things. If you're talking about being diabetic, but what happens if you're just trying to lose weight and ketosis and watching your different things that are in your blood just to track to find out whether you're getting surges or not. I don't know what else you can measure in your blood with something like this other than glucose, but longer term, like once you got a sensor in your camera, you can start using the software to say, oh, these things mean this, right?
Yeah. And I know you always ask this question, how long?
Yeah.
I was prepared this time. So based on the factors that in the article, like we're looking clinical trials beginning like this year, next year, FDA approval the next 2 to 5 years, manufacturing scale up the next maybe 4 to 6, and then commercial launch maybe as early as like 5 to 8, 9 years. But again, it's an estimate based on where they're currently at and a whole bunch of different things. But like when it comes to FDA approval, the approval process for a new medical device like this often takes 3 to 7 years. So there's a few more hurdles, and then we got manufacturing scale up that needs to be done.
That's
right?
why
So,
I think we'll see it faster. I know I know it's counterintuitive,
yeah.
but because that takes so long, we're going to see this type of technology faster because right now this is coming out of a university. Somebody's going to come along and say, "Hey, I've got a crap ton of money. I'm going to buy this and I'm taking it to the next level." And great, I'm not going to call it a medical device. I'm going to put it in the next Google Watch or Apple Watch or whatever.
Yeah.
And we're just going to start doing it. And we're going to do all this tests while we're doing this stuff on the back end. So by the time we get the FDA approval, we're ready to go and it's already in 100 million users' hands.
Yeah, exactly.
That's why I'm just kind of like, we can now call it a medical device. We've been doing this all along.
Yeah. For now, we'll
but
just call it something else and then get it into the hands of people.
It's for hobbyists. It's for people who want to
Yeah.
track their own whatever. Yeah. So I think
Yeah,
that's why
sure.
we'll see it faster because this has been the holy grail for so many companies for so long to get this non-invasive optical. And then you can do so many things with it. It wouldn't be long whether it's a medical company or a technology company that comes and says, no, we'll buy that.
Yeah. Oh yeah, for sure. It'll be like what's the big one that has the glucose monitors? Jesus, they have a big office in Mississauga. Anyways, yeah.
I don't know who they are. Pardon?
One of those companies.
Yeah, I did a bunch of work for Apotex way back in the day as a pharmaceutical company, but there's a bunch out in Mississauga. I didn't even know until you
Dexcom, but that's not the one that's out there. There's another one, but
until you go in and work in that area, you don't realize that this is like literally a bunch of like a whole area of pharmaceutical companies, just a bunch of them. Yeah, there's
every single one is there. GSK, GlaxoSmithKline, yeah, all of them are there. Yeah.
I didn't know until I did some software development for them. So it was interesting way back in the day.
Yeah.
This has been great. You got any final words on this?
No, this will be cool. Yeah. And the other company I was thinking of was Medtronic. They're the ones that have the office in Mississauga. But yeah, really cool stuff. Really interesting. Super excited to see. Well, this one is a little bit more realistic than the other two that we were talking about, except for the Trillion transistors. I know we've got we do have that 3D architecture that's being developed that there is potential already. So yeah, really interesting to see where we go from here. But one thing was I would like to see, maybe I'll develop it, is I would like to have a dopamine sensor for me to measure my dopamine levels. That would be great.
Indeed. It'd be interesting to like insulin resistance, you probably get a dopamine resistance in it, and it's you have to probably kind of figure out the right balance. You get a dopamine hit every time someone likes something on Twitter or social media, and you do this and you do that, and there's 1,000 different things, right? Plus, it maybe eat the food you want or whatever. So it's hard to. That's an but I definitely that is something that's needed as well.
Yeah, for sure.
So, John, you help startups, technical companies, anybody with 2 developers or more find funding for their startups. What do you got going on, and what's the latest in startup funding?
Yeah, so there's a bunch of announcements made in the budget, so we'll have to see what comes out of that. I'm working on a summary right now, but yeah, I help companies across the board. I'm working with a agri company right now, and a bunch of others all across the board, clean energy, different things like that. So if you're a Canadian company, or even if you're not Canadian company, if you're incorporated in Canada, feel free to reach out. But yeah, that's I help with Shred is the best one to take advantage of because you're entitled to it. It's a tax credit, but there's tons of other grants and potential funding out there. Non-dilutive funding, I must say.
And people should reach out to you on LinkedIn?
Absolutely. Yeah. Send me a message on LinkedIn. I'll send you my Calendly and we'll set up a call.
And you got anything going on next couple of weeks?
Other than Startup Drinks on May 2nd, I've got an actual, this is really cool, fractional C-suites and consultant private dinner put on by Ryan Wong, who's a phenomenal guy. That's coming up on Tuesday of next week. So I'm excited for that.
Yeah, you're supposed to send me these links ahead of time so I can pull them up for people.
Yeah, no, yeah, I know. I just thought of it right now. I apologize. Yeah,
I know. I try to
in the
Google these
morning.
things, but we go through. I know, same thing. Right, it's one of those things. That's great. Sounds wonderful. Where do you know where they can find that? What do they Google?
So
What do they?
that one's invite only, unfortunately. But
Okay.
that's but there's other ones that Ryan puts on that I will talk about as they come up. So yeah, there's some cool stuff.
And we'll get links in there so you can find where it is.
Sure.
Check out all our stuff at torontostarts.com. That's where you get the FutureTech podcast that comes out. We're behind on releases, just so you know. We've actually got 42 episodes recorded, not including the 3 that'll come from this, because you mentioned that last week, and we've got like a 10 to be released that are all ready to go. I was slow releasing. I was doing 3 a week, and then I went to 1 a week when we switched my editing tool, so it took me a little while. But now I'm back. I know what I'm doing. Everything's good. So you'll see 3 episodes a week and maybe a little bit more as I'll start pumping them out until we get a little less of a buffer. So you'll see more of those. If you're stuck in your business and you're looking to move ahead, you're having struggling with sales, finding clients, anything along that lines, go to startupcoach.ca, book a discovery call with me. We'll help you get unstuck and move to the next level. You mentioned on May 2nd, our Startup Drinks TO, we've got almost 50 tickets gone already. So it's going to be a great night. We're still just over 2 weeks away. Join us there. It's open bar, open pitch. You get 20 seconds to pitch. We have investors, founders, industry experts. It's a warm and welcoming environment. Everyone's going to give you advice and help you and connect. You always meet valuable connections, but it's not always what you think, the ones you think. And, I've talked to people as they're leaving. They found new business partners in this and that and the other thing. And it's always a great conversation. So hope to see you there. And we'll see you guys all next time on FutureTech.
Thanks so much.